Hello everyone, so welcome to the second lecture of week 9. So we have been discussing about prompting, and in this lecture we will just delve a bit deeper into why in context learning setup of prompting actually works. Now we will present certain hypotheses and see what the previous researchers have found in this aspect. Specifically, we will talk about a very popular induction height hypothesis on why in context learning actually works, the connection within context learning, and we will end this lecture with talking about certain counterintuitive effects. Right. So, this is something very interesting in this particular study. So, that is what will be today's lecture. And then we will continue talking about some advanced prompting techniques in the next lecture. So what does in context learning stand for? Typically, what we have seen, we could. So, the language model is already pre-trained, right? So, this is where we are. So, language model is already pre-trained. Now, at inference time, so this is very important. This is always we are talking about inference time. So, at inference time, during just the forward pass, that is, we pass the input. So, we pass the prompt, right? So, we give the prompt, everything we want, we can put in the prompt, and we do not do any gradient based updates. So, there are no gradient based updates to the model parameters. Just in the forward pass at the inference time, we are seeing that is the model able to do certain new tasks, right. Can it predict tokens better, and in general can it reduce their loss, right. So, that is what we are saying. So, we are free to give things inside the prompt that we are giving in the forward pass only, but we are not changing model parameters at all, right. So how will that impact the model's performance on doing new tasks, right. So, that is the idea. So, can the model do new tasks just based on what we are giving it as an input at the inference time, right, not changing anything in the model parameters. So there is a very prominent hypothesis on how the model is able to do that it is so what it is able to do. So, we give the prompt, we give it some examples, and now given a new input, it is able to produce the output for that, right. So that means, so something like, so you are giving some instruction and you are giving some input, corresponding output, input 1, output 1, input 2, output 2, and then you are saying, okay, my input, and that is where you stop your prompt, let the model produce an output. So the hypothesis, if I summarize it, it says something like that given this input, it tries to use its format to find out what is the similar thing it has seen in the context. So, it will go to all these inputs, right, previously, and see after that what was the output that came in. It will try to copy this format here, right. So, something like the label is the space of the input, it tries to see where is a similar distribution of words coming in the context. So, find similar distribution in the context, and then what comes after that you try to copy, and you copy what comes after that, right, very simply. Okay. So yeah, that is the induction hypothesis. So, you see an example here. So you are in your model at this point. So, you have seen words till now, you have to now predict the next word. So how does it predict the next word? It will try to match. So, wherever it is finding a similar prefix. So in this context, the same vintage word has occurred previously. So, it tries to match, and there it finds the word cars and copies it, right. So, it is little more refined than what I was saying. I was saying that given the word vintage, it will find vintage and see what comes next, but it is directly finding the next word, cars, right. So, something little more interesting is happening. It is not going to vintage and then finding cars, it is directly finding the next word after vintage, right. And that is what you will see how it happens in the induction, using the induction head hypothesis. And it finds and copies it to the next location, right. So, the function of the induction head is to predict repeated sequences, right, and this you can generalize to different kind of patterns, right. So, you have an input corresponding output, you follow similar format and then you copy based on the output, right. So, like I mean to put it simply, suppose you are seeing this pattern A, B and there are certain things in between and then A. In the input sequence, what it will do? It will predict that B follows A, right. So, it has a completion rule immediately that A, B something, then you have an A, then you get a B after that. So, this is happening just in context. So, whatever example is getting in context. So, this is the learning that is happening, that by giving examples of input output, you can, given a new input, you are able to copy, right, what kind of output I will do. So, this is just for direct copying, but you can generalize it to more say copying kind of distribution, the tasks and so on, the formats. Right. Okay. So, how did people study this? I mean, they studied in a very specific setting. I will not go into too much detail, but I will talk, I mean, at least something that will give you an idea how this phenomena is happening, right, actually using these induction heads. So, this is the name of a circuit, a transformer circuit. So, some sort of abstract component of the transformer network, and so it's part of the attention computation, and you can discover it just by looking at one or two attention heads. Right. So, we will just look at one or two layers in the transformer network. Okay. And this was the first paper that talked about that from Anthropic. So, a mathematical framework for transformer circuits, and they talked about these circuits and the induction head hypothesis there. So, what is this idea? So, let us go to the transformer architecture, but looking at a slightly different angle. Right. So, actually if you have read our transformer chapter from the SLP3 book, it talks about a residual stream. So, each token has a separate residual stream, right, because each token has its own path. So, remember, I mean, so what you do, given a token, you first embed it. Embed can be position embedding plus word embeddings, and then what you do, you try to look at all the words. So, like if it is a decoder, you will look at just the past words, right. So, how do you look at that? Using query from this word and key and value from the other words. So, key are used to looking for the words, then once you know which words to attend to, you take their values and then using WO matrix you compute. So, and you may have multiple attention heads. So, each attention head is run and you are adding the output, right, to the residual stream, and then you apply an MLP and you get another output, but the same token. Yeah, this is a residual stream that is going on. And when you go to the end of the layer, you apply an unembedding layer, and that is where you get the logics, right. So, for each token you have a residual block, and there are interactions happening through between the residual streams of multiple tokens via the attention mechanism, right. So, you can see this residual stream as simply the sum of the output of all previous layers and the original embeddings. Okay. And the attention heads are moving information across streams. So, you have a token A, token B residual streams, and this multi-layer, this MLP, what it does, it will simply continue, right. So, within the same residual stream, but the attention head will go across. Right. Attention head, what they do? So, you will, for example, here this is token A, this is token B. So, what you will do, you will for getting the output token A, what you will do, you will take the query from here, and the keys will be taken from all the different tokens. So, you are reading information from multiple residual streams, and then you are so you are able to copy information from the residual stream of another token, right, and you write back to the residual stream, right. Now, we will do something here. So, we will say, okay, when they write back, they write to a different subspace. So, we will talk about some subspaces in the embedding, right. So, they write to a different subspace than what they are read from. Okay. So certain important notions for studying this. So, the central object we are talking about the residual string, right. For each token there is a residual string, right. Now, different heads in each layer can be thought of as operating independently of each other. So, they are reading and writing into this residual string, right. That is what is happening. Your different heads are reading from there, writing back, and these heads can compose to form circuits. So, for example, so we call K composition when the output of one head is used to generate the key vector in the attention calculation of a subsequent head, right. That is what we call as the K composition. Now, so we are having three matrices, so query, key and value, and we will say we are reading from or from the residual string, and WH can be used for as writing to, right, into the residual string, because you read based on WQ and WV and WK, and then you see what part of WB it will go, and then multiply with WO to actually write it back into the residual string. So, you actually also can talk about two different kind of circuits. So, you have QK circuit, so query and key circuit. So, you can combine the query and key matrices together, call it WQK, QK circuit, and so what it will do, suppose you have the jth token, so and you want to say how much attention ith token is paying to the jth token, right. That is what we are saying. So, we will have query from the ith token and the key from the jth token. So, you can use this idea to say, okay, how much attention the ith token is paying to the jth token, right. So, conceptually what this matrix is telling us, so because you are paying attention to the jth token, you will move information from jth token to the ith token, right. So, information is moved to and from, right, moved from jth token to the ith token, right. Similarly, the other two matrices, the WV matrix and WO matrix, you can still combine them, call them the OV circuit. Now, here you are defining a mapping from this vectors, residual string vectors to another residual string vectors. So, what is the mapping? So, you see here you paid attention. So, ith token and the jth token. So, ith token paid attention to the jth token, right. Now, you will take the value for the jth one. So, you will take the value for this, multiply with OW matrix and write it back to the ith token, right. So, you can have a mapping. So, you have Vj here in the residual string vector at the jth token, and what you do, you multiply it with this OV, right. So, you have this multiplied by WOB, and that is the vector that is getting moved from token j to the token I, right. So, this is what is getting moved, Wj and WOV is what is getting moved to ith vector. So, this matrix is telling us, the OV circuit is telling us what information is moved. So, hey, this one is telling us information is moved from which token to which token, right, moved to and moved from, but actually what is the information exactly that is being told from this WOB, right. So, what information? So, this is moved to and from, coming from QK circuit, and OV is telling us exactly what information is being moved, right. So, yeah, I mean that is another abstraction of this idea of query, key and value and WO matrix. So, now let us focus on some subspaces in this residual stream. So, what is happening? So, we are starting a residual stream, we give the embedding, we give the positional embedding, then we keep on adding more and more information, right, and of course, we will take a very simplified view here. So, the hypothesis is that there are 4 different subspaces, right, and each one has a different interpretation. So, for example, so you have in the green color you have something for token encoding subspace, just the embedding, right, and we will say this token is x, just to make it very explicit we will say this is the token information, this token is x. These are the embedding matrix rows. Then you have the positional encoding subspace, this token is at position x, right. These are the rows of position matrix. Now, you also want to decode finally, right, what is the next word. So, you have a decoding subspace, so that the next token will be something, will be x, right, that is a decoding subspace, and these are columns of your unembedding matrix that you apply at the last layer. And you also have a previous token subspace, that is like what was the previous token. So, this is like intermediate information. So, everything intermediate information you will put in here. So, what all you have seen, the previous token was this, or whatever else you have seen would come here. Right. So, you can think of these 4 subspaces. And when you start here, you may not be using all the subspaces at the same time. So, when you start, first of all you get the word embedding. We are calling it IM. So, suppose the token is T, IMD, right, to make it explicit, that is the word embedding. And you have the position embedding. So, then you have at position 0, right. So, you add both of these, they are going to different subspaces, IMD at position 0. Of course, you are adding them, but assuming they are orthogonal, you can actually decompose this information. So, they are going into different subspaces, right. Now, and of course, we will say there will be some notation for. So, when you multiply the one hot vector to the embedding matrix, you get IMA, the embedding for this, and similarly for at position n is equal to something, right, at some position. Okay. So, that is how we are starting, and we will talk about 4 subspaces. So, token embedding, position, the decoding, and the previous token. So, now, so when we start, what happens? We only feed the sequence, and we will have a very simple example. So, we have Dursley. So, we will have D is 1 byte pair, I mean, right, H per byte pair encoding. This is 1 token, then URS. Similarly, in this stream, somewhere else, I mean, in this sequence, you again have D and URS, right. And we want to see how after D you will predict URS, right. And right now, out of 4 subspaces, you only fill, when you start, you fill only 2 subspaces, that is the word embedding. So, I am D, I am Urs, and so on, and I am at position 0, I am position 1, position n plus 1. Okay. So, what happens? I mean, you start from the first one, the layer 0, that is you have just passed the embedding, and then you are applying this query key value. So, what happens? So, we are here. So, D URS, D URS, you are just feeding this, right. This is what you have to predict, right. You have to predict this. So, we will see how it predicts the last URS, right. So, let us say, so what will happen to the URS token, the one that is at position 1. So, its word embedding is something, I am Urs and I am at this position. So, what will happen? So, you will get a query to represent this word. I will get a query from here, right. So, query comes from here, and I will look at the previous token. So, that is D. So, key comes from here, query and key comes from here, right. And I get the dot product, I get the out, and I get the corresponding value from here, right. And then I come multiply it with the output matrix and put it in a new subspace. So, what do we get here? So, at this point, the QK circuit is employed. So, right now the query vector is I am Urs at position n plus 1, right, and this WQ, the matrix, what it does, it says, okay, in the 0th attention head, what it is doing, it is saying, okay, I am looking at just the previous position for you, right. So, I am at position 1, so I am looking at previous position. How do I do that? You can simply rotate, because assuming the sinusoidal and other kind of embeddings that are based on rotation, let us say you are simply doing some rotation, the position embeddings that are based on rotation. So, doing some rotation. So, you are saying, okay, I am looking for position, the previous position, right. Otherwise, there is no concept of position otherwise. So, you have to do some rotation, and then you can look for the previous position. So, and just at the previous position, this is the corresponding key I am D at position 0, right. After some rotation, you can find from the subspace, you do rotation, you can find out the corresponding one at the previous position, right. You understand there is no explicit position in the transformer, there is position embedding only, right. So, you can rotate and you can get the previous position. So, you get the word at the previous position, right. And when you so you do a dot product and you get a high score typically, because this key would be a good match for the query. That is what happens in the QK. So, now what will OV circuit do? Now, OV circuit will say, okay, so you will read information from the key I am D at position n equal to 0, right. It will multiply with the WV matrix to get the corresponding value, and then WV matrix to say what is the final thing that I am going to write, right. So, now because you have a high attention, you are reading from here, and what you exactly write is very interesting, is that okay. So, you see I will write something to this particular word, right. I am currently focusing on us. So, what I will write, which word am I following? So, I write I follow D, right. So now the word you us itself has a subspace information that I follow D, right. So, this is what is the summary. So, each token looks one position backward, yes, and gets the information about which token precedes it. So, it does not have an explicit position information, but using the rotation it can find out, and then it says okay, I'll put that in my subspace that I follow D. So, each token is putting this information I follow D, or I follow this token, I follow this token, right. Okay. So that is what is happening layer 0, right. Now, what will happen at layer 1 attention head? So, now this let us look at this T. Of course, it would have also done the same thing at the layer 0. It would have read I follow whatever word was before, it would have added it to its subspace also. But what will happen at the layer 1, right. So, layer 1, now we want to focus on this particular instance of D. So, the query will come from here. I am D at position n, right. So, it is a separate position. So, that is where the query is coming from, and let us say it will actually focus on, it will actually query, will multiply it with the key of this word, also key of this word, right. But let us focus on what will happen when it actually interacts with the key of ers, right. So, the key is I am ers at position n is equal to 1, I follow D, right. So, at this first layer, what is this query? So, remember the 0th layer, what was the query? I am looking for the previous position. So, this is my current position, minus 1, I am looking for position 0. So, that I can add to my subspace, I follow this word. In the next layer, I am not doing that, I am doing something else. I am looking for a token following D, right. So, very interesting, I am looking for a token that follows D. That means I am looking for a token which has already stored in its subspace I follow D, right. So, that is why I do not have to go back and match this. I only can directly match a token that has stored that I follow D, right. That is the interesting part here. So, I am looking for a token following D, and this has anyway stored this information I follow D, right. So, this is my query, I am looking for a token following D, and this has a good match because I already have this here, I follow D, and so that means yes, a high attention. Now, that means now next the OV circuit will come into play. We will see what do I write from here to this word, right. So, what OV circuit will do? So, it will read the token information, right, and will convert into something which will result in okay, you have to have the next word as ers. So, what you write, this is for the unembedding, right. So, remember there were 4 subspaces. So, this will go into the unembedding subspace, that is the next token is ers, right, and this gets added to the substring. Of course, there would have been something I follow, right, there will be a blue colored subspace I follow something, but that is not what is important. What is important that this is added to the unembedding subspace, right, and yeah, and this will eventually increase the probability for us getting predicted from this token. So, that is what is happening. Okay. So, putting everything together, yes. So, you have at the 0th layer, so you pass the word embeddings and position embedding. So, I am only up to D, I am predicting ers, right. 0th layer, what is happening? The attention head at 0th layer does something interesting. It tries to rotate it so that it goes to the previous position. So, this goes to the previous position, so that it gets a good match, and then the OV circuit will write what is the word that comes before. So, it writes I follow D. So, its position stream is residual stream is writing I follow D, right. Now, for the first layer, this word, the QK circuit, it will search for a token that has information I follow D, right. It searches for I follow D. It finds I follow D here. So, it has a good match. So, puts attention, and then what it writes in the unembedding subspace, the next token is ours. Right. So that's the idea, and then so you apply an embedding matrix to that, and you get the high probability for ours. Okay, so let's revisit now. I mean, this was very interesting concept hypothesis for induction hat. So now going back to the formal definition, we can define induction hat as one that will exhibit the following two properties on a repeated random sequence of tokens. So one is prefix matching. So the head attends back to the previous token that were followed by the current origin tokens, right? Like here, suppose these were category 40 IDs node instruction, and you are here category 40 IDs node. You have to predict the next token. So what will this token do? It will directly find out which token has in itself the information that I follow node. So this will have I follow node. Node, or I mean the previous things that I have seen, right? I follow node or whatever is the context, right? So it will go there and it will copy so that the heads output will increase the logits corresponding to the attendant 2 token. So it will increase the logits for instruction. So probability for instruction goes up. That's what is happening. So so that means induction heads are any heads that are empirically increase the likelihood of a token B given a sequence of A, B followed by some words in between, then an A. So it will increase the likelihood of B by doing this kind of interesting pattern matching. Okay. Okay. So actually in this, so this was the second paper from the same group. So where they talked about in context learning and induction heads, and they made various interesting arguments and presented experiments and analysis that why do they think this induction heads are there some empirical, so this was a hypothesis, but are there some empirical evidences of these, right? So what they said is that in their experiment they found something very interesting, that when you continue pre-training transformers, so they undergo a phase change. So during training they undergo a phase change during which the induction heads actually form, and the in context learning improves. So there is a very interesting phase change that happens, and this is the kind of plots that they show. So this is for one layer. So if you have a one layer network, it will not happen. So you need at least 2 layer or more, right? So if you have 2 layer attention only model, so they found after some amount of training there is a drastic phase change, and they are saying in this phase change is where the attention, this induction heads develop and your in context learning ability improves, right? So only models with more than 1 layer have an abrupt improvement in the in context learning, and this is the phase change, right? So period of training in plots to make comparison between the plots CG, right? That's what they have done. So how are they what are they actually plotting here on the y-axis? So x-axis is about how the training is going, so how much training has happened. Y-axis, what are they plotting? So they are plotting something very interesting, that is the loss for the 500 token in the context minus the average loss for the 50th token in the context, right? So they have a context in which they will take the 50th token and the 500 token. So what is the loss for this, and what is the loss for this? So this is L500 minus L50, right? And typically the loss for the 500 token may be higher than what you have for the 50th token, because that is much far, right? But what they found, this difference, it's decreasing, right? So decreasing of difference is what you want. So we are able to predict for a large context word, right? And why they did that? Because this 500 token, I mean the choices were arbitrary. They showed they can vary this and does not change too much. So this is near the end of the 512 length context, and 50th token is enough far so that it has seen the title and everything, right? The initial instruction and some basic properties of text it has already seen, right? So this is how much the loss changes, and they say they approximated by the in context learning behavior of the model, that okay, so if this loss is decreasing and this happens abruptly after certain period, that means that the in context learning capability is developing in the model. And they found, for example, so there were evidences for that. For example, this is the sequence where you have Mrs. Dursley, and then Mrs. Potter. That's the sequence, right? Now they are seeing what happens to the loss for Potter, right? And they found that the loss for Potter after this phase change has increased. Why? Because what will happen, I mean this message after this phase change will start looking at the word that says I follow message, right. So, it will have this D token, it will start predicting D token with a high probability, Potter will have low probability. So, the loss for Potter will actually increase, right, during the phase change. On the other hand, if we have the Dursleigh, for this Lage, it will go back and find out where this Durs or whatever context is there. I mean, whichever token says I follow this, and it will start predicting Lage with a high probability. So, this its loss decreases, right, after this phase change. Right. So, this is what there's some nice very evidences in the paper. Okay. So, they made certain arguments, for example, the mechanistic plausibility of induction head. So, they say that for small models they can explain how these induction heads actually work, and they can even show how they contribute to in context learning. So, and then they make an argument that what is the continuity from small to large language models. So, while they have shown everything in the small language models, there are many behaviors and data that are related to both induction heads and context learning that are smoothly continuous when they go from small to larger models, right. So, that means the simplest explanation of why this is happening is because of induction heads. So, this is not directly seen, but in the experiment, then when they start modifying or then increasing the size of the language models, they continue seeing this behavior, and that is the hypothesis. This actually happens in the large language models also for the same reason. Okay. Now, the certain more phenomena that we will quickly talk about. So remember, in context learning, the main thing we are seeing is why this few short examples actually work, right. So you see, we give some examples and then we ask another input, let it predict the output for that. Now, there are many interesting questions. For example, which examples to choose, right. In my set there may be multiple examples, which one to choose? Can I take some random examples? Then if I take some 3 examples, should I put them in this order? Or if I change the order, will something happen? And do I need all the labels? Do I need the correct labels? I mean, there are many questions. Now, there are certain interesting, certain counterintuitive things that people have found in the literature. Now, I will talk about just some of these. For example, what is the importance of the order in which you can put them? So, in this particular paper, fantastically ordered prompts and where to find them, what they found that they did experiments over this 2 data sets. So, GPT family over SST2 and some data sets. They found that, so you see what they were doing. So, they had 4 shot, right. 4 shot means you have 4 examples. Now, you can put them in any in terms of permutation 4 factorial. So, there are 24 possible orders among these 4 examples, and they are seeing what is the standard deviation, right. So, what they found interestingly, I mean, there is a huge difference across in the accuracy across these 24 different variations, and this is what they conclude, that they suffer from order sensitivity. So, the same prompt for the same prompt, the order in which the samples are provided can make the difference, right. So, some particular order may give you state of the art, some may give you just the random performance. And this finding they found across tasks, across model sizes, prompt templates. So, this was very, very interesting, that I mean even the order matters how you can put that. Then there are also some very counterintuitive effects. So, this paper, rethinking the role of demonstration, what makes in context learning work. What they found, so they had 2 different task classification multi choice example, and they used multiple kind of LLMs with various sizes. So, what they found, so for example, interestingly, no demos means a 0 shot, right. So, it's a 0 shot, you do not give any examples. So, and this is the few shot. So, you give demos with the correct labels, and few shot was always doing better than 0 shot, right. So, that was very clear, few shot is always higher than 0 shot. But then they said, okay, what if I give the same demos, but remove or so just put the labels randomly. So if I say the sentiment, instead of saying positive, I can say negative, neutral, or I can just say put another English word, right? What will happen with that? So interesting, they found, of course, when you put random labels, the performance is lower than the gold labels, but it is still much higher than the zero shot. So that means what is important, the demonstration. You give demonstration, even if your labels are not correct, it still does better than zero shot. That was something very interesting that they found. So that's why I'm calling it some counterintuitive effect, right? Now the paper has a lot of details. Of course, there are limitations on the study, but so for example, they said, okay, what if, so this is all the labels are correct, only 75% of the label are correct, others are incorrect, 50% are correct, 25% are correct, and this is 0% correct, right? And this is no demonstration. And you can see, even if you go gradually from 100% to 0%, there is a gradual decrease, but very minute decrease, right, in the performance. So performance improves when you give all the labels correctly. But even if you don't, even if you just provide examples, right, with wrong information, that's better than not providing information, like not providing any examples. This was something counterintuitive. So and they also said, okay, what if I change the number of k, if I give more examples? And they said, oh, this gold and random, the curve is very, similar across k. So gold is always better than random, but the difference is not so high. And yeah, it's not that you can keep on giving more k and you get a better performance. After some time, the performance also decreases, right? So yeah, this was something very interesting. Now yeah, there are more details in the paper, but they tried one experiment, that why does it actually work, right? So they said, okay, there may be 4 things. So one is the format, right? So you give the format, the input output format. So one is the format, then the label space, that you give the actual labels, the positive, negative, neutral for sentiment and so on. Then you actually give the correct input in the input distribution, and then you give the mapping correct, input and label mapping correct, right? So which of this is more important is what they wanted to say. Is the format important, label space, input distribution, or multi input label? So they tried multiple variations. Like gold label is where you are given everything, right, and that has the best performance typically, right, throughout. Then what if the mapping is not correct? That means you replace it by random labels. You actually give the same examples, but you replace random labels by some random labels, right? You still give the label space correctly. Label space is correct here, right? The same positive, negative, neutral, but you change the put them randomly. So then you see the performance is slightly lower, but it's still the second highest roughly, right, across. So this is important. That means the mapping may not be so important, but everything else is important. Then they say, okay, what if I give some out of domain data with these random labels? What happens then? So out of domain means some random sentences. You preserve the format, right? You preserve the format. You still preserve the labels. You know what labels to give, but the input is random. Right? Input is random, and label are also random because we don't know the labels for them correctly. So, but this is from the label space. So then you see the performance is still, yeah, sometimes it's okay, and sometimes it's poor. Right? There is a lot of drop. Okay. Then what if I give random labels only? So I don't preserve the format, I don't preserve the input and all. So their performance is even worse. What if I do not give the label space? Right? That means when I say a sentence, rather than saying positive, I can say something else. Fantastic. That's not in the label space. Interestingly, that gives quite good. So that means what seems to work is you give the format. Right? Format is important, and the input is correct, right? And this actually somehow corresponds to your induction head hypothesis. That is, see, even if you are giving the label wrong, right, the input is correct, so it will start storing I follow this, right. So, and whenever you have the new input, you can go back to saying which one says I follow this, right. Now the label is wrong, so you can't copy this directly. So that's another interesting thing, like you can't copy the actual label because the label is wrong. Then what do you actually copy? So where does because see, you have already learned all this in your pre-training. So do you go back to your pre-training sometime? So that's interesting question. But this is important that format is something you have to preserve and input is something that you have to preserve, and that gives quite good. Yeah, and then there were other things that do not do as well. Yeah, but still, yeah, gold labels to the best. This was more of understanding of why in context learning actually works. And yeah, I would say there are hypotheses, and they have shown some very interesting arguments have been given. But yeah, it's not still clear which of these actually makes in context learning work. Okay, I mean, yeah, these are the two main papers that you may go through. They give a lot of details about the circuits and their experiments. And next lecture, we'll talk more about some advanced prompting techniques. Thank you.